If we look at the sky and at its infinite depths in the night, the universe seems to be motionless. But the universe moves endlessly, and what we can see, the stars, the 100 billion galaxies, the interstellar gases, are only an infinitesimal part of it. All the rest is invisible. And among all the mysterious invisible objects in the universe, there are the black holes, according to the suggestive definition of what is left of a star. A black hole is the proof that gravity has overcome all the other forces. Nothing can escape from a black hole, not even the light. During the first half of the 20th century, all the astrophysicists rejected this idea for decades, regarding it as an impossible oddity. Sir Arthur Stanley Eddington, the most famous among them, used to say that nature would prevent this nonsense. Nowadays we know that in the universe there are millions of these cosmic monsters, and that one of them, gigantic, is placed right at the center of our galaxy, the Milky Way. The black holes are breaches of space-time. They are also the fueling engines of the brightest objects in the universe, the quasars, star clusters more radiant than 1,000 million suns. Many scientists now think that in these space-time hollows they can find the clues to understand the universe thoroughly, its laws, its evolution, and its probable end. The study of black holes has pushed our knowledge of the cosmos to the furthest limits. Inside them, the ordinary physical laws could be completely overturned. Within these gravitational cavities, atoms are so much crushed that they overstep the last frontier of nature, represented by their own existence. And the two great scientific theories of the 20th century, the general relativity that deals with the infinitely large, and the quantum mechanics that explains the infinitely small, are one in front of the other, unable, though, to reach a proper synthesis at the moment. The discovery of black holes and the outstanding research started by human beings to understand how stars come to life, live and die, have their prominent figure in a great Indian scientist, Subrahmanyan Chandrasekhar, universally known as Chandra. On the morning of the 1st of August 1930, at the wharf of the Peninsular and Oriental lines in Bombay, there was the usual confusion of any departure. A magnificent gate overlooked the docks, the Gateway of India, a monument erected by England some years before to be the symbol of its entry into the Raj. But that was going to become soon the sad witness of its leaving. From the beginning of the 20th century, many shipping companies decided to increase their sea links with Europe, and Bombay had become an important intersection. The great steamers shuttled between the European and the eastern ports, their travels made easier by the recent opening of the Channel of Suez. The Lloyd Triestino had already set up a line between Venice and Bombay, Linea Celere India, with regular travels more or less every 2 weeks. Near the pier of the steamer Pilsner, a small crowd was gathering. There were friends and relatives come to bid farewell to a young boy heading for Europe. Subrahmanyan Chandrasekhar had the solemn gait of a Brahmin, but his glance was a blend of hope and sadness. Among all those hugs and kisses, he was missing the embrace of his mother, left home seriously ill. She had encouraged him from the very beginning, pushing him to set out on that journey to England, to the temple of science called Cambridge. He knew that he would not see her anymore. At last, the ship left the docks. The profile of the large colonial hotel, Taj Mahal, and the Gateway of India slowly became just small points on the line of the horizon. Chandra was leaving behind him the greatest country of the British Empire, pervaded at that time by a political turmoil. India, the place where so many cultures mixed together, the country where he was born and raised, the country that placed in him all its hopes for the future of science. That 2-week journey modified the course of astrophysics and changed Chandrasekhar's life forever.
Chandra was born in Lahore, which is now in Pakistan. His father had just gotten the job as the Auditor General in Northwestern Railways. And so they had just moved and he was born. He was the eldest, first son in the family. He had 2 more sisters. This was October 19, 1910. For the first 5 years, they stayed in Lahore and mostly taught by his parents at home because they were in this area different from their culture, from South India, in the northern India, Lahore in Punjab. And then 2 more years they spent in Lucknow, and then they moved to Madras, and then he went to regular school.
For Chandra's family, the chance to return to Madras came in 1923, when the foundation stone of the new, comfortable house known as Chandra Vilas was laid. Chandra used to spend a lot of time in the cool family library, reading with great passion books and books of mathematics, many written by his grandfather. In the surroundings, there were very few houses, but in one of them lived a girl whose name was Lalita. Ayyar, Chandrasekhar's father, was an authoritarian parent. He chose the husbands for his daughters and decided the careers for his sons. His greatest aspiration was to see his eldest son follow his steps and find a position in the colonial government service. However, Chandra's interests were completely different. He didn't mean to pursue a career in the government service of the British Empire. He was an enfant prodige, deeply interested in science and mathematics, strongly influenced in this inclination by his mother, Sita Lakshmi, an open-minded and sunny woman. She told Chandra these simple few words: "Don't listen to your father. Don't let him press you. Just do only what you like."
Chandra had determined right from the high school days to become a scientist, pure science. And he was influenced by his uncle, Sir C.V. Raman then. He had not won the Nobel Prize yet, but he had made the discovery, sensational discovery, which came to be known as the Raman effect. And his uncle had given up a big government job and pursued pure scientific research and had become famous. Another childhood incident was his mother. When he was 10 years old, the great Indian mathematician Srinivasa Ramanujan died, and it was in the papers. And his mother had mentioned that such a great mathematician, he went to England and he became famous, and he came back and then he died. And so that influenced him quite a bit in his early years.
In the whole history of Indian science, Ramanujan was the first Indian to get the recognition from the West. You see, there were, of course, many excellent mathematicians before, and now people are unearthing more and more of them. But that was the time when when India was sort of disconnected intellectually from the rest of the world. But Ramanujan was the first Indian to gain recognition from the West when the West was in the real height of its powers. He was the first Indian, for instance, to be elected to the Royal Society, FRS, and that became a big deal in the country.
The beginning of the 19th century was an extraordinary time for the Indian science. Besides Ramanujan, there were great scientists like Saha, Bose and Raman, whose scientific successes strongly inspired the young generation that was growing up in the colleges. This golden age of the Indian science aroused a great interest in the Western scientific community, and many important scientists used to come often to India. Here we see Robert Andrew Millikan engaged with Raman in a balloon experiment on the cosmic rays. At that time, Raman, Chandrasekhar's uncle, was already one of the most famous Indian scientists, and he was going to win the Nobel Prize in Physics in 1930. Literature was also extremely lively, and Tagore was the towering figure of Indian poetry. In those years, India witnessed an extraordinary political ferment aimed to reach independence from the British Empire. Gandhi was the charismatic leader of that complex struggle. Saha, Raman, Bose, all the great scientists of India were all deeply involved in the independence movement.
So, but there was a great struggle, and these people were also motivated that to demonstrate to the West that given proper conditions, they can just be as good as any Western scientists and so on. Their motivations was partly this nationalist movement, nationalist struggle.
And I think it took a while for the country to feel proud about itself and reawaken itself. There were many instances outside of science which kindled all this. And one thing that the British did by reforming the education was to actually provide opportunities for very good people in the country, youngsters, to really come forward and think independently. And I think this created a cadre of people who were really outstanding, Raman, Bose, Saha and others. Chandrasekhar belongs to a little younger generation, of course. And then they were full of nationalism, idealism, and were working towards their science without necessarily politicizing it to some degree.
During those troubled years, Chandra decided to study physics and enrolled in the Presidency College in Madras, at that time the best university in the country, where nearly all the teachers were English. His career was outstanding, and he became quite famous for his skill in science subjects. He was able to read and digest books and books of physics and mathematics with the utmost facility. He was absorbed in reading a science classic, the treatise Atomic Structure and Spectral Lines by Arnold Sommerfeld, in which the author disclosed the principles of spectroscopy and quantum mechanics. Chandra had the chance to meet Sommerfeld personally in 1928 when he came to India and delivered a speech at the Presidency College. He arranged a meeting with him.
So he makes an appointment to go and see him in his private room in the hotel. Sommerfeld asks him, what have you studied? And Chandra replies, oh, I have studied your book, Atomic Structure and Spectral Lines. Sommerfeld said, oh, well, no, that's all old now. That book is no use. There's the whole new quantum mechanics has come about. People like Schrodinger, mentions Schrodinger, Heisenberg, Dirac, and all the changes that have taken place. So there's new quantum mechanics. So Sommerfeld then looking at the crestfallen, as Chandra describes himself, this encounter. And then he said, what else have you studied? Or he said, oh, well, I have studied statistics, Boltzmann statistics. And Sommerfeld immediately said, oh, that's also no use anymore. There's a new statistics now, Fermi-Dirac statistics and Bose-Einstein statistics, the statistics based on new quantum mechanics.
In the second half of the 20s, a great revolution in atomic physics was taking place in the most important laboratories across Europe, thanks to the brilliant intuitions of Max Planck and Niels Bohr. Quantum mechanics, with its counterintuitive consequences, the uncertainty principle by Heisenberg, the wave equation by Schrödinger, the probabilistic interpretation given by Born, disclosed new and amazing perspectives for research. In 1929, in October, Werner Heisenberg, who was at the time 28 years of age, went to India to give a lecture at the Presidency College. He was already a celebrity, and he was considered a possible Nobel Prize winner. This meeting, that sealed a strong friendship, had a remarkable importance in the life of young Chandra. During that period, Chandra began to study The Internal Constitution of the Stars by Arthur Stanley Eddington. In this book, the great English astrophysicist led the reader to the outermost frontiers of astronomy. We can reasonably think, Eddington wrote, that in a near future we will be able to understand such a simple thing like a star. Chandra was deeply fascinated by that challenge. Although they look eternal, stars are mortal. Like everything else in this world, they come to life, grow, and then die. Depending on its mass, the birth of a star can require hundreds, thousands, or millions of years, just a twinkle of an eye in the immensity of the universe. The stellar nurseries are the icy regions of the stellar nebulas, the Orion Nebula, the spectacular Eagle Nebula, or the impressive Great Cloud of Magellan, all of them made of the simplest and richest gas in the universe, hydrogen.
La formazione stellare avviene da un gas di composizione.
The main feature in the stellar formation consists of a gas with a simple chemical composition that concentrates around some points where its density is already higher. Here, the gravitational force causes the collapse of some notable clouds of this gas.
Delle nubi, diciamo, significative di questo gas primordiale. Aumentando la pressione.
With the growth of temperature and pressure, what can happen is that the hydrogen atoms fuse together into the next element, which is helium.
Fondersi, diciamo, e creare, diciamo, quello che è l'atomo di.
Through this process, nature is able to produce energy. This nuclear fusion is, for example, the fueling energy of the sun.
È fatta in modo che è in grado di produrre, diciamo, dell'energia. Questa è l'energia sostanzialmente che sostiene, ad esempio, attualmente il Sole. L'energia che io ricavo dalla sintesi
The energy coming from the synthesis of hydrogen in all its forms, the emission of photons, the convective motions, one can think of a pan with boiling water, counterbalances the force of gravity that tends to contract the star while increasing its density.
in ebollizione, diciamo, cose di questo tipo qui, insomma, serve a contrastare la gravità che tenderebbe, diciamo, a far diminuire continuamente le dimensioni, diciamo, della stella e aumentare la sua densità centrale.
This process, in which the hydrogen is burnt into helium, is the one that keeps the stars along the main sequence.
Diciamo, il processo che tiene sulle stelle.
Our Sun, for instance, is a star of the main sequence.
Il Sole, diciamo, tipicamente è una stella che è in sequenza principale.
As these nuclear reactions go on, the stars acquire a multiple layer structure resembling an onion. There is a central core where the nuclear synthesis develops, and then there are external layers of decreasing density, where the furthest one is the so-called stellar atmosphere. All this structure has to be in equilibrium.
Per mantenere, diciamo, no, la struttura in vita contro la gravitazione viene appunto fornita dalla nucleosintesi.
Stars can greatly differ for dimension, mass, as well as temperature, that is, for the nature of the light that they emit, the so-called spectral classes. The systematic analysis of these properties started at the beginning of the 19th century with the Danish astronomer Hertzsprung. Using the available star catalogues, Hertzsprung noticed that stars of similar spectra could yet greatly differ for their dimensions. The relevant difference, he realized, was in their densities rather than in their masses. The astronomers started to introduce the terminologies red giants and white dwarfs to refer to stars, where the first class referred to stars with a radiant surface much larger than the second ones. Taking into account new data on optical spectra, around 1913, the American astronomer Henry Norris Russell discovered some intriguing relations between the light emission and the temperature of a star. First of all, Russell stressed that there were the spectra of 100,000 stars and that the great majority of them fell in 7 classes. Each class may be regarded as a measure of the temperature. Such a grouping was already an interesting discovery because it showed that an enormous number of stars just fell in few spectral classes. But according to Russell, much more interesting was the remarkable regularity that emerged when the luminosity and the temperature of the stars were displayed on a diagram. The output was a fascinating representation of the firmament. This was a huge leap forward in understanding stellar evolution. Indeed, it was soon clear that what appeared to be a static representation of the universe was instead an intriguing chart of the different phases of the life of a star. Why stars populate certain areas of the diagram and not others? How do they move across the diagram? Eddington introduced the expression main sequence to indicate the diagonal line of the diagram, now universally known as Hertzsprung-Russell diagram. The majority of stars in the galaxy, including our Sun, are all main sequence stars, namely stars in the middle of their life. However, not all stars were aligned on the same sequence. There were two large groups that were far away. Which were their characteristics? At what moments of the life of a star these two groups were referring to? The first group was the one of the red giants, stars of low temperature but high luminosity for their enormous size. The stars of this group have exhausted the supply of hydrogen in their core and have switched to fusing hydrogen in a shell outside the core, expanding then enormously. This is just the first step toward the extinction of a star.
When the part of fuel represented by the hydrogen is over, helium takes its place, turning then into carbon. This process takes place at a much higher temperature, so there is a stage where the core contracts and the temperature reaches 100 million degrees, while the production of energy increases dramatically.
Outer shells of hydrogen start burning, helium is formed right there, and through the heating of nuclear reactions, the stellar atmosphere begins to expand. In this way, a star turns itself into a red giant.
The expansion causes a decrease of the temperature of the outer layer of a star. This stage is known as the phase of the red giants. Why red giants? Because the diameter, if compared with the former stage, is 100-200 times larger, and the temperature makes its color turn from white and yellow into red. Now let's remember that the color of a body depends on its temperature. The higher the temperature, the shorter the wavelengths of the light emitted, so that a white or a blue star is hotter than a red one.
Dipende dalla sua temperatura. Quanto maggiore la temperatura, tanto più avviene l'emissione a lunghezze d'onda più brevi, cioè verso l'azzurro. Quindi una stella bianca-azzurra è più calda di una stella rossastra.
The second group was made of stars with high temperature but faint luminosity, the so-called white dwarfs. They were thought to be stars at the latest stage of their life.
After the red giant stage, the external shell becomes so thin that through millions and millions of years it spreads in the interstellar medium. The only part left is the core, a very small core, that has a diameter comparable to that of the Earth and a very high temperature, so that it radiates a white, blue-white light. It has become a white dwarf. Dwarf because it is very small, white because it is very hot. So we can say that a white dwarf is a corpse still warm. And the mystery was how this contraction can come to a halt and what happened to a white dwarf at the end of its existence.
Cosa succedeva ad una nana bianca nella fase finale della sua vita.
The white dwarfs were a real anomaly. Why had they a temperature so high but a luminosity so low? At that time, Mount Wilson was the most important observatory in the world, often visited by important scientists like Albert Einstein. Using the large telescope of Mount Wilson, Edwin Hubble made in 1929 his important discovery about the redshift of the farthest galaxies, an indication that the universe was expanding. In 1914, the astronomer Walter Adams was analyzing the exceptional behavior of the binary star system made of Sirius and its companion Sirius B, nicknamed the Pup. Sirius is the brightest star in the sky, and for its luminosity it obscures almost completely the light of its companion. But Adams, using a new sophisticated technique, was able to overcome the problem and to analyze Sirius B as well. Its mass was comparable to that of the Sun, but its luminosity was 3,000 weaker. An oddity that had an amazing explanation. The companion of Sirius should have a tremendous density, since a mass comparable to the one of the Sun was squeezed in a volume 50,000 smaller. This means that a spoon of the material of such a star would weigh like an elephant on Earth. How could it be possible that matter could have such an incredible density? Which laws of nature stood behind this bizarre behavior? At the beginning of the 1930s, white dwarfs were a big puzzle for astrophysics. In those years, Chandrasekhar was involved in the study of Fermi-Dirac statistics. He'd already published a paper on the proceedings of the Royal Society, thanks to the attention of Ralph Fowler, so he came across a fundamental work of Fowler on white dwarfs.
And just at the same time, Fowler's paper appeared. Fowler's paper was another revolutionary paper at the time because it applied the new quantum mechanics to the theory of white dwarfs. Chandra understood that paper, and also at the same time, because Fowler had referred to Eddington, he read the paper, he read his book on internal constitution of stars and applied Eddington's theory of what is known as polytropic theory of how equilibrium under gravitational forces. Applying that, he prepared a paper which showed more details of Fowler's theory.
Just while he was devoting himself to this branch of science, Chandra was unexpectedly offered a scholarship by the Indian government to continue his studies in England. Due to his acquaintance with Ralph Fowler, he decided to go to Cambridge to work with him on his PhD. Finally, Chandra had his great chance. Everybody expected a lot of him, as his uncle Raman had written in one of his letters. "We all can't wait to see you doing for physics in India what Ramanujan did for mathematics." At the Presidency College, they promised him that once he'd come back, he would become one of their professors. His mother was already seriously ill, and Chandra hesitated between leaving or not, since he'd been told that she could die at any moment. But with great strength, she pushed her son to set out on that journey to England, telling him, "Chandra, you were born for the world, not for me." Chandra left with a sharp pain in his heart, but with his head full of plans for the future. Above anything else, he was thinking of those puzzling white dwarfs, a very interesting problem that had caught his fancy during the previous months. On the morning of the 1st of August 1930, the Pilsner, a liner of Lloyd Triestino, left Bombay and headed for Aden. The steamer crossed the Arabic Sea, the Red Sea and the Channel of Suez, continued across the Mediterranean heading for Brindisi, and finally docked at Venice on the morning of the 16th of August. That voyage changed the course of astrophysics forever.
So after some time traveling on this long voyage, first there was seasickness and rough weather in the Arabian Sea and so on. When everything calmed out, he began to think about his paper. Particularly, he had deduced that Fowler's theory required the density in the center should be 6 times the average density. So he quickly made a calculation and found that indeed if the central density is high as it is, and if you take special theory of relativity into consideration, there will be a limiting mass. The mass of the star that could become a white dwarf could not exceed a certain limit, and that limit could be expressed in terms of fundamental atomic constants.
Quello che Chandrasekhar capì e che elaborò proprio.
What Chandrasekhar understood and developed during his journey from India to England was that a degenerate gas could not sustain a mass larger than 1.4, the mass of the Sun.
Massa superiore a 1,4 volte la massa del Sole. Masse più grandi cosa avrebbe?
Larger masses would cause a gravitational collapse, further squeezing the star.
Schiacciando ulteriormente la stella.
Il collasso va giù. La materia,
when a star collapses, its equation of state changes. Through photodisassociation, the atomic nucleuses break, and the electrons, once free, become extremely important.
liberi, diventano estremamente importanti, e qui avviene la prima grande.
The great idea of Chandra was to apply to the gas of these electrons the principles of relativistic quantum statistics.
I principi della fisica quantistica e statistica.
He found out that a stellar structure can last as long as its mass does not exceed a certain limit.
Il corpo centrale poteva essere tenuto in piedi purché la massa non superasse, un limite.
The fate of a star strongly depends on its mass. If the mass is less than 1.4, the mass of the Sun, the star is destined to become a white dwarf, namely a very compact object the size of the Earth that shines like a diamond. In this case, the enormous gravitational force is contrasted by the degenerate pressure of its electrons. This pressure is a direct consequence of the Pauli principle, a quantum effect that forces electrons to have different speeds. These motions give rise to a pressure of completely different nature if compared with the pressure of gases, subjected to the classical laws of thermodynamics. This degenerate pressure is the only one that can counterbalance the gravitational weight of a white dwarf. But for stars of larger masses, this equilibrium was no longer possible. This was the striking conclusion of Chandrasekhar. The mass of a star should have a limit value. But what could happen to a star if at the latest stage of its life its mass was larger than the limit value? Would it go through an endless process of gravitational collapse with all its mass concentrated just on a single point?
Questo introduceva, un concetto che
This introduced an idea that was formally developed by Laplace in the 18th century. The idea of black hole is strictly linked to the escape velocity of a body that depends on its mass and inversely on its radius.
Per ogni corpo possiamo definire una velocità di fuga, d'accordo, che è legata.
This velocity is the one necessary to get away from the gravitational field of a body.
Quindi massa grande e raggi molto piccoli.
The greater the mass, or the smaller the radius, the higher is to be the escape velocity.
Uscire, dal campo gravitazionale dell'oggetto, via via più grandi. E
if there are no limits to the ratio between the mass and the radius, the escape velocity can equal the speed of light.
Uguale alla velocità della luce. E questo è il concetto poi essenzialmente di buco nero.
This essentially is the concept of black hole, i.e. an object so compact that the ratio, where g is the gravitational constant, m is the mass, r is the radius, and c is the square of the speed of light, is almost equal to 1. This was the great innovation introduced by Chandrasekhar. The limiting mass of a star, because there was no other physical process able to sustain its structure.
The idea of critical mass introduced by Chandra was absolutely revolutionary. It was revolutionary because at that time the general opinion was that the mass of a star could be arbitrarily large. So it was inconceivable that a star with a mass exceeding a certain limit could not exist.
This idea was not only revolutionary, but in a way almost heretical, as Chandra had the chance to see when he arrived in Cambridge, the temple of science in England. With its colleges, Cambridge was, together with Oxford, the very heart of the English academic world. Oxbridge was the word that could describe properly that particular environment, recalling immediately the gloomy but solemn atmosphere that filled the corridors of those centuries-old universities. A world supported by antique traditions and by an academic etiquette built on unwritten but strict rules, which were applied either in the conversations or during the ritual of the afternoon tea. The formalism of introductions is really excessive, and compared with its implications, it's not worth the trouble, Chandra wrote in one of his first letters to his father. On his arrival at Cambridge, Chandra had a shock, probably the same experimented by the great Ramanujan years before. His sense of loneliness was increased by the difficult situation in India and by the racial prejudices that were very strong in England at that time. Moreover, he felt the bitter consciousness of being absolutely insignificant in front of such famous scientists like Paul-Adrien Dirac, Ralph Fowler, Arthur Stanley Eddington, who used to teach in those colleges. Eddington was the most prominent figure in the astrophysics of those years and was in control of the key academic positions. Under his influence, astronomy had ventured as far as unexplored regions, both in the observation and the theoretical fields.
Eddington at that time was the internationally famous astronomer, and also because he was one of the principal, he led an expedition to test Einstein's theory of relativity, the reflection of light, and had concluded he was responsible to verify Einstein's theory, and so it required a great international fame. Also, his popular books were very famous, Nature of the Physical World, Pathways to Science, and he was a great popularizer of science, and also wrote this famous book. I think it was the first book on relativity, which was the English-speaking people tried to learn theory of relativity. And the theory of relativity was supposed to be so difficult, so there was a feeling that only 3 people understood Einstein's theory of relativity.
Eddington was the incarnation itself of the traditions at Oxford and Cambridge colleges. His dresses were accurately shabby, he was ruthless and arrogant in any skirmish, and the cruel witticisms in his words cut like a razor blade.
Chandra saw Fowler and showed him the paper that he had worked, how he had extended his theory. Fowler was very happy with that and immediately sent it for publication in monthly notices. But this idea of limiting mass, he was skeptical. And he said, oh, we better send it to Milne, Edward A. Milne, for see what he thinks, because this was really a remarkable discovery if that was the case, and there must be something. So it was sent to Milne, and Milne kept it. He did not respond, whatever. So it went about a year after, Chandra decided on his own to send that paper to publish in the Astrophysical Journal in America, because he did not receive any reply. And after some corrections, that paper was the critical mass was published in 1931. Wanted some comments, but he did not receive any comments.
Interacting with that academic world was very difficult. To overcome those hard times, Chandra made himself follow some stern rules. He woke up early every morning to work hard all day long. There's nobody here I can talk to. Mathematics is my morphia. It makes me forget everything else, he wrote to his brother. His mother died when he had yet to finish his first year in Cambridge. Her death came as a great shock to him. Ironically, this happened the day before his first meeting with Eddington. At that time, he started realizing that in physics there were a lot of brilliant scientists who were making important discoveries, while nobody paid much attention to astrophysics. He felt discouraged because, in spite of all his hard work, he didn't succeed in producing anything relevant. So Chandra went to discuss with Dirac, who confirmed the lack of interest in astrophysics. Dirac himself pushed him to spend a year in Copenhagen so that he could get close to the latest discoveries in theoretical physics. The atmosphere was completely different there. The young and the old mixed together, and Niels Bohr was a source of inspiration for everybody. In Copenhagen, Chandra met all the outstanding scientists of the time. He began a close friendship with Victor Weisskopf and Leon Rosenfeld. The year in Copenhagen passed in a flash, so he returned to Cambridge, and after 3 years he sat for his PhD examination.
Fowler and Eddington were the examiners. He gets his degree. And then what to do next? He wanted to go to Oxford and work with Plaskett and further in astrophysics. But in any case, he had also applied for a Trinity Fellowship, and he was not sure at all that he will get the fellowship. It was not, no Indian other than Srinivasa Ramanujan had gotten this fellowship for the Trinity. A fellowship in Trinity was one of the great, it was very, very difficult to get that fellowship. He was not at all optimistic. So in fact, he had packed and was ready to go to Oxford, and as he was going, just by chance wanted to go and look, and to his great surprise, he had won the Trinity Fellowship, and that completely changed his life according to him.
Thanks to this event, he felt much more confident. He could stay in Cambridge 3 more years, and with an additional year, he could find a proper job on his return to India. In the autumn of 1934, Chandra started to work very hard to develop a complete theory on the terminal stage of a star and on the limit value of its mass. He was, apparently, encouraged to follow this project by Eddington. The old astronomer used to stop and discuss his work and got him a hand calculator, a true rarity at that time, to carry out the calculations necessary. Chandra wrote a very detailed paper and was invited to present it at the meeting of the Royal Astronomical Society of London, the most important circle of the English astronomers. The meeting was scheduled for the 11th of January 1935 in the afternoon.
Chandra was sure, had complete theory, there was no question, he had solved all the problems, any doubts that were there. And so just before the meeting, usually the Royal Society meetings, notices came just a few days before the meeting, and Chandra used to frequently, right from the very beginning, he used to attend these meetings in the Royal Astronomical Society in London. So he knew the secretary, and he gets the program on Thursday, the day before. And to his great surprise, he finds that Eddington was going to give a talk soon after, exactly after his talk. And the title of his talk was Relativistic Degeneracy.
Chandra was astonished and wondered why he didn't tell him about it before. Eddington used to go and see him very often to talk about his work all the weeks before. He thought that Eddington was going to tell him what he was going to talk about, but this didn't happen. That evening after dinner, Eddington came up to him and told him, "Your paper is very long, so I've asked the secretary to give a half hour for your presentation instead of 15 minutes. Chandra thanked him. The next day, before the meeting, Chandra and McCrae were waiting together when Eddington came by, and McCrae asked him,
"Professor Eddington, what is this relativistic degeneracy you're going to talk about?" And Eddington looked at Chandra and said, "That will be a surprise for you," and went away.
When his turn came, Chandra explained his theory rather brilliantly, pointing out that if the mass of a star is 1.4 larger than the mass of the Sun, this can't evolve into a white dwarf. He introduced a diagram to show how the radius of a star could vary according to the variation of its mass, and how the star itself would collapse with a radius equal to 0 if its mass is close to that of the Sun. What does it all mean? Would the star annihilate? Would the force of gravity swallow it? Chandra ended his speech in a confident tone. A massive star cannot evolve into a white dwarf. We must depict a different fate for it. He was very proud of his work. He sensed that his discovery of the limiting mass of a star, beyond this limit the star is swallowed by the force of gravity, was really an important achievement. He didn't have to wait long for Eddington's reaction. That was incredibly violent. A real slap in the face.
And after his talk, the president invites Sir Arthur Stanley Eddington to give his paper.
I do not know whether I shall escape this meeting alive, but the point of my paper is that there is no such thing as a relativistic degeneracy. Dr. Chandrasekhar has got this result before, but he has rubbed it in, and when I discussed it with him, I felt driven to the conclusion that this was almost a reduction ad absurdum of the relativistic degeneracy formula. Various accidents may intervene to save a star, but I want more protection than that. I think there should be a law of nature to prevent a star from behaving in such an absurd way.
After making these remarks, he then tries to explain what is wrong with Chandra's theory, makes some inscrutable arguments about standing waves and progressive waves, and makes a humorous comment about the president, etc., etc. Anyway, he cavalierly completely dismisses the whole theory, and Chandra was just left dumbfounded, humiliated, as people passed by him after Eddington, and everybody said, sorry, sorry, sorry.
Quest'idea Eddington la trovò orrenda, orripilante e criticò aspramente.
Eddington found this idea almost heretical and strongly criticized the young Chandrasekhar. Possibly also his youth played its part.
Era un fatto che incuteva poca fiducia nel grande Eddington.
La vicenda con Eddington ha dell'incomprensibile. Eddington era il padre dell'astrofisica, il padre rigoroso.
The clash with Eddington was somehow unbelievable. Eddington was a prominent figure of astrophysics, respected and renowned among the scientists of that time. And it's absolutely puzzling why Eddington used his powers so heavily to pin down Chandra. Furthermore, he behaved very unfairly. At the conferences, he asked to talk after Chandra, only to have the chance to state that Chandra's ideas were just stellar absurdities. No doubt Eddington was cruel, and Chandra suffered a lot for the situation. This controversy influenced Chandra's life very deeply.
Chandra was shocked. His whole world was crumbling around him. He realized that years of hard work had been publicly dismissed by the most distinguished astronomer of the time. But Eddington's opposition went on even after that famous meeting on the 11th of January 1935. He carried it out in many other circumstances, sometimes even preventing Chandra from speaking. But Chandra knew that his theory was correct. The great Eddington was wrong this time. He tried to find assurance from the other physicists.
Pauli says Eddington does not understand physics. And Dirac says that he does not find anything wrong with Chandrasekhar's theory. So all these physicists were completely supportive, but nonetheless none of them wanted to come out and say Eddington was wrong.
Eddington's prestige was so high that nobody dared to talk openly against him. Chandra was left alone, and during the following years, no one supported him in public. In 1940, he wrote to his father, "I feel that all the astronomers, no one excluded, think that I am wrong. They look at me as if I were a kind of Don Quixote trying to lame Eddington. I'm facing a very depressive experience. My only way out is to change the branch of my work. Together with the white dwarfs, Chandra left behind him the British Empire. He went to the United States in 1936 to cover a position of professor at the Yerkes Observatory at Williams Bay near Chicago. He was not alone in his travels to the New World. Lalita went with him. She was the girl he'd met during his happiest years in Madras. They got married in 1936 and they spent a happy life together. Because of his clash with Eddington, Chandra developed his personal style in scientific research. His first aim was always to achieve a thorough knowledge of a particular subject. Chandra dedicated to every topic 7 to 8 years of intensive, almost monastic work that invariably ended with the writing of a monographic book. Then he turned to another field of research. Chandra was a very appreciated teacher. He explained everything with extreme clarity, writing equations on the blackboard in an elegant handwriting with his long fingers. Among his students, we can find C.N. Young and T.D. Lee, awarded with the Nobel Prize in Physics in 1957 for the parity violation. To meet with him, he didn't hesitate to drive a couple of hours in the snow. He had the chance to cooperate with Enrico Fermi in 1953, a great pleasure for him since they complemented each other perfectly. In the meantime, something very meaningful was happening. Astrophysics was making a rapid progress thanks to the improvement of the observation techniques. In 1967, the first neutron stars were discovered and identified as the stage subsequent to the white dwarfs. Chandrasekhar was right. Not all the stars could rest in peace like the white dwarfs. Furthermore, it was possible to extend the idea of critical mass to the neutron stars, and for those with a mass 3 times larger than the mass of the Sun, the fate was dramatic. They would turn into black holes. The conjecture of the complete gravitational collapse, introduced for the first time by Oppenheimer and Schneider in 1939, found its definitive ratification in the works of Archibald Wheeler, Roger Penrose, and Stephen Hawking. And in 1967, Archibald Wheeler was the first to call this dramatic gravitational collapse black hole. Soon the first evidence came through observation. At the end of the 60s, we detected a powerful X-ray source inside the constellation Cygnus. That source marked the presence of a black hole, today known as Cygnus X1. Nowadays, on the basis of the observation of X-ray and gamma rays coming from the universe, 300 supermassive black holes have been discovered in our galaxy, and 100 more in the neighboring galaxies. But their number is probably far higher. There may be millions of them in each galaxy. Chandra had waited for years, discouraged by that regrettable episode with Eddington, before again approaching the problem of the gravitational collapse and the black holes. And he did it as only he knew how. The imposing volume, The Mathematical Theory of Black Holes, written during the last years of his life, is one of the cornerstones of science. In Chandra, the scientist never obscured the man. His deep love for culture was witnessed by his equally passionate studies in the fields of painting, music, and literature.
Last time I saw him was at the 100th anniversary of the American Physical Society. There was a special lecture by Chandrasekhar on this Principia, his book on Principia. I don't remember. It was somewhere in Atlanta, I think. He was going back to Chicago and I was going back to New Haven, but we took the same flight. And I was sitting on this end of the aisle and he was sitting on the other end of the aisle. And then as we traveled for a couple of hours, probably I dozed off in my seat, whereas before I dozed off and after I woke up, I could only see Chandrasekhar reading some fat book in front of him. To me, that was amazing.
When Chandra was awarded with the Nobel Prize in 1983, more than 50 years divided that day from the discovery made in a cabin of the Pilsner. And the sadness in Chandra's eyes was the only thing left of that 20-year-old boy, so full of dreams and hopes.